make like a high throughput screen, right? Just to put all the structures into.
So we already can use it for the geometries. So the ground state calculations are pretty good.
For the few structures you got.
Huh?
For just few structures which you used before.
We using it's I forgot the name of the group. It's Lindsay. There was a group. We met at ACS conference. There is a lady. She's working on applying the semi-empirics to the ruthenium complexes.
Oh, okay.
And she was parameterizing the, I think it's PM6 or something like this for ruthenium complexes. And then Levi was taking her parameters for ruthenium and kind of tune it to see how it works for iridium. So for the ground state calculation, just finding the structures, we have very good results. They provide pretty much similar geometries to the regular DFT, and they're about 10 times faster.
So you got kind of the same geometries, but what about the energy-wise?
For excited state calculations, of course, it was very wrong. Like we having completely different, like new peaks appearing somewhere, like very strange. But now she is published recently. She published a paper where they really applying it to the excited state DFT calculation.
So she did some Martin twisting.
Yeah, so they already parameterized it. So it's not PM6 anymore. It's really kind of new semi-empirical approach. And so Levi is actually kind of, we discussed with him that he probably needs to tune now those parameters for this new excited state semi-empirics and see maybe we
They have the PM7 now, semi-empirical, which is much more improved in compared to PM6.
She was using 6. But
would
specifically for metal-organic complexes. Well,
we have this
in
now
cases,
Gaussian 2016, it has probably PM7 inside. Okay, so not opening on the big
Oh, it will be on this video screen.
on the,
I can call for tech support, but it will be a waste of time. Better everyone can see this video screen.
So there is not much to discuss. I'm just gonna some refresh the information what we discussed last time, right? And then really discuss.
Can you
what
refresh
problems we
us
have.
what is D3SC?
It's
Data-driven.
yeah, this 3D. It's a 3D data-driven
Development.
in science and chemistry, something like that. No, it's not a design, data-driven design. It's science and chemistry, right? So these, according to the, the NSF letter, so they wanted to have a few projects which exactly fits to that idea, data-driven science. So kind of using large data, maybe not big data, but kind of large amount of data, and extract some useful scientific information, some kind of mechanism, some kind of properties which can be useful for quick design of new materials. Okay, so that's right. That's how our the main steps kind of split. But this what we wanted to discuss last time. Kind of was expecting some intro from several groups. Actually, it's kind of resembles few sections of the project. So the computational studies, the synthesis, and cheminformatics, some kind of data generation based on the experimental data and the computational studies. That's the objects. mainly what's gonna be investigated, but mainly it's gonna be ruthenium and iridium, right? That's what we put in proposal. So as you can see, there are several applications for these kind of materials purposes. So mainly it's for the imaging and for sensing.
Yeah, it
For different
bioimaging,
sensors.
yeah, because we target on developing organometallics with near infrared emission,
Yeah.
so that's for bioimaging application.
For bioimaging applications. Mhm.
And we have another application I think we wrote in the proposal is by using the nonlinear absorption for the eye sensor protection.
Mhm.
That's another, it's called the optical limiting application. So those are the two
main
applications.
the bioimaging, these are sensor
Sensor protection,
protection.
yes.
Mhm. So these the objects. What I wanted to discuss this time, if you can quickly.
We also included platinum complexes. Ruthenium, iridium.
Oh,
and
the platinum. Yes, the platinum over there as well.
Yeah.
Yeah, so that's good. I mean, we have some kind of diversity. That's good for this data-driven stuff. So the more diversity you have, the better to catch some
Right.
kind of some features which are responsible for each particular.
Yeah, whether it's a
class.
common feature or because the difference is for platinum is a square planar complex, and the iridium, ruthenium, they are octahedral complex,
They are-
more spheric.
Right.
Yeah. So the major difference between ruthenium and iridium is iridium has a strong ligand field, so their d orbitals are much more deeper. It means the d orbital, the highest occupied orbit, d orbital for the iridium complex has lower energy than the ruthenium. Or in other words, simplified, for ruthenium complex, their frontier molecular orbital has more contribution from the d orbital of ruthenium. But the iridium complex, depending on the ligand, the d orbital contribution could be much less.
Mm-hmm.
Yeah, so I know even in literature and even in the beginning when we started working on this, some reviewer even asked, there are lots of ruthenium complexes that have been started. The iridium complex should be similar to that. That's not true. So we just actually, this year we published a paper, we did a direct comparison using exactly same site, yes, of ligand. Because the most commonly reported ruthenium complex, it has a 3-diene ligand, 3NN ligand. But for iridium complex, the most commonly or easy to synthesize one is we call it monocationic iridium complex. It has 1 NN ligand and 2 CN ligand. So when the ligands are different.
Structures maybe?
Oh yeah, sure.
There is a small whiteboard and
Okay.
hopefully we can project it.
Yes.
So we can draw on it over here.
Yeah.
That's great. Yeah, that's what we need actually.
Try to
I wanted to
understand the
discuss, the
difference,
structures and also what kind of properties we need to extract for each structure. What the difference between them. Oh, that's nice.
Okay, that's good. So I need to draw it in a better way. We have this. That's the octahedral structure. So we basically have nitrogen here. It's cross. Okay, let me just give me a second.
We also have this. on this screen, if you need some of the ligands,
Oh,
you can get from here.
okay. I think I'm fine. So here should be, I just draw it in the wrong way. Here is the carbon. That will be the nitrogen. This is for iridium complex. The CN ligand basically mean it's the simplest CN ligand will be this phenylpyridine. So it's this carbon and then nitrogen. This carbon initially a benzene ring, it has a hydrogen, but when it coordinates, this hydrogen is deprotonated. So this carbon actually carries a negative charge. Okay, iridium here is a iridium 3. It's a 3 plus. So in the complex, the carbon here and the carbon here, each of those carries one negative charge. So it balances the charge. Overall, it has nitrogen is coordination bond. Nitrogen uses a lone pair to interact with the vacant orbital on the iridium. So those are called coordination bond. It does not balance any charge.
So it's usually positively charged.
Yes, it's monocanionic. It's also commonly we call it being cyclomethylated. For the CN ligand coordination is called cyclomethylation. Okay, so we have two of the CN ligand and the two nitrogens on the two CN ligand. They need to be crossed. That's the general geometry. But for ruthenium complex, ruthenium is ruthenium 2 plus. Okay, so here is a 3 plus. And it has also similar octahedral structure, but it has 3 NN ligand. NN ligand is 2 bipyridine. Okay, so one here is another, is 2 bipyridine we refer.
So you cannot use exactly the same ligands for the ruthenium?
Now, okay, let me explain that. It's very difficult to synthesize ruthenium
With these
things.
okay.
Yes.
But for iridium, you can actually have everything also with bipyridines, right?
Yes,
It's not an
ruthenium
issue.
we can use 3 bipyridine as a ligand, but it's also difficult to synthesize. But we were able to make it. It's very rare.
No, but for
Are we
iridium,
taping it?
Yes.
you can do both either with NC or NN.
Yeah, that's
ligands.
right. Okay, let me just still draw the general structure here. Okay, so ruthenium, no.
So it's difficult to synthesize that, but as soon as you synthesize, it's quite stable.
Yeah, it's stable.
Stable.
Yeah, it's stable. So yeah, ruthenium, that's the common feature, common coordination pattern with the 3 diimine ligand. We call it N ligand, we call it a diimine ligand. I think in recent years, literature also reported we can it can use 2 diimine ligand plus 1 CN ligand, so you get a plus 1 ruthenium. That's possible, but it's rare. Means it's difficult to be synthesized. For iridium complex, the most commonly started one is this monocanionic one. It was used, it has the phosphorescence, means emission from the triplet excited state. And by varying the structure of the either diimine ligand or the CN ligand, we can adjust the homo-LUMO level, we can adjust the excited state energy. Therefore, the emission color could be tuned. So the monocanionic iridium complex is widely started for OLED application. Okay, there are certain companies already produce the green emitting iridium complex or the red. The blue one, iridium complex, that's quite rare because you need to, because for the iridium complex be able to produce blue light, it's need to be, the emission need to be come from the ligand, one of the ligand. Okay, that's
So we can
difficult
tune
to
it.
push. Yes. So that's the beauty of iridium complex because it has 2 different type of ligand. When you adjust the diimine ligand, basically we try to adjust the LUMO. When we adjust the CN ligand, we try to adjust the HOMO. Yeah.
So for the ruthenium, are all 3 And then ligands the same?
Could be the same, could be different. You
So-
can put a certain substituent on one of the one or two of the diimine.
So do you still go through the chlorine salt like you do for iridium? Or do you not, like where you have the two metal centers connected to chlorine? Or is it a different mechanism?
It's a different synthetic approach. What Levi is asking for is how to synthesize this. To synthesize the iridium complex, we need to use the CN ligand to react with the iridium trichloride first. Then will give us this di-iridium, chlorine-bridged dinuclear iridium precursor. Then we use that precursor to react with the diimine ligand. Then we break the chlorine bridge, then convert it into the mononuclear complex.
So the majority of them are all three the same, or you have two the same and then one different?
No, here
for the
only
ruthenium.
two are the ruthenium. Ruthenium, the commonly started one would be either all three. That's called a homoleptic complex. If all three ligands for the ruthenium are identical, homoleptic. If they are different, most cases are two the same. The third one is different. Okay, for iridium complex actually, okay, iridium complex, another commonly started one is this called trace cyclomethylated iridium complex with 3CN ligand. That's a neutral complex, okay, because again here, each of the CN ligand carbon here has a negative charge, so overall it's a neutral complex. The neutral one actually is the most started for the OLED application. Monocana ionic one, some people use that is for the electron chemical luminescence, CCL or LCC, LECC, light emitting chemical cells, chemical cells. Yeah. So, yeah, that's a general feature. As I said, the iridium complex, either the neutral one, trace cyclomethylated one, or the beans cyclomethylated monocana ionic one. Those are the two types most easy to be synthesized and started. But for ruthenium complex, the most started one is the trace diimine one with 2+ charge. Okay. Then I think can we go back to this screen?
All right, we can.
Push the computer on this.
Oh, for computer.
The PC.
PC. Okay. Yeah. On the first structure, what you see there is a beans terdentate ligand. Okay, what I just showed you, just draw there. It has 3 bidentate ligand. Okay, here is 2 terdentate means 3 atoms. One ligand provides 3 atoms to either coordinate or form organometallic bond. Okay, so the both iridium and ruthenium can form complex like this. The ruthenium one actually is still the more well started one than the iridium, because for iridium the synthetic part is
So
quite
returning back when you're saying the difference between these complexes in kind of, without going to the details in the structure, the ligands, the coordinated bond is stronger with ruthenium rather than with iridium, or backward?
let's see.
For the same ligands, let's say, if you can compare.
Okay, I actually did not check the bond strength, but what I'm talking about is the ligand field strength.
Oh,
Ligand field strength
so the
is
splitting in the
yes,
electronic level.
how the metal split the ligand field.
And the ligand field is stronger in ruthenium than in iridium?
No, in
Or backward?
backwards.
Iridium is stronger, so
iridium
you have
is
stronger
yeah, larger
splitting
splitting,
levels.
yeah, between the 2D orbitals. Therefore, if you have a larger pi conjugated diimine ligand in the iridium complex, your frontier molecular orbital will have very little contribution from the metal. But for ruthenium complex,
Much stronger.
the metal, yes. So
And,
it
usually,
has,
and it's also ruthenium is more redshifted, right?
yes,
Typically.
because the d orbital is higher, so the lowest singlet excited state in the ruthenium complex typically is the metal to ligand charge transfer. So it's more redshifted and stronger also.
From this point of view, if you're looking for infrared emission, then ruthenium is a better choice than iridium then.
But the thing is, in most cases, ruthenium, the emission quantum yield is Quantum yield is smaller than the iridium.
So it's kind of given the right range of energies, or more promising range of energies.
Not so
Yeah.
strong.
But
Not-
in terms
not
of
as-
lifetime and intensity, it's weaker.
Yeah.
And again, because of the MLCT character, very strong MLCT character, probably.
That's right. Then if you really, extend the pair conjugation of the ligand, you can really switch the triplet excited state. Because here we talk about two things. Absorption is mainly based on the singlet excited state. Emission is from the triplet excited state. So the adjustment of the singlet and triplet
Might
can
be
be
different.
completely, yes. Then the triplet, especially when the pi conjugation of the ligand becomes more extended, the triplet excited state can become the ligand localized pi star triplet state.
Right.
Yes.
And you saw it already, right?
Yes.
In several cases.
We already saw it in many cases. And also when the pi conjugation increased, it was interesting. It could be the lowest triplet state is the ligand localized pi star state. But the emitting state is a higher triplet excited state, T2. Yeah, it's not the T1. It's sort of
But is it bad? Because then you're kind of trapping it. Like if you have anything below, then your emission is not 100%. You trap in some portion on the slow state anyway, right?
Yes, that's right. It certainly can go through from the T2 to T1. Then T1 is non-emissive,
And you lose
so it definitely. And if your emission comes from T2, the lifetime will be shorter. Quantum yield will also be reduced. Yeah, but we saw in many. It's not very common, but we saw it. It's not
Some
that
kind
rare.
of trend.
Yeah, we saw many
It
cases.
looks like we
like
can relatively
They already
kind
know a lot of
estimate.
things about these guys.
It's
Right.
just based on the calculation, like looking at the single state and then triple state, we can estimate the energies what we are looking for, right? I mean, we can
And it's the
look for
thing
some
is specific. We know how to
energy
tune it. Yeah, the challenge is when you actually lower the triplet state emitting state to lower than the energy gap law, the non-radiative decay will become much faster. It's exponentially increase. Then
In case you increase this conjugation lengths on the side
on the ligand.
chains.
Another way how we can think about it, do we want to increase the spin orbit coupling? I mean, it's typically strong in the systems, right? But probably we can also think about doing the substitution on ligands, and maybe not just pure organic ligands, but maybe also think about, like, I don't know, having bromium as additional atoms on the ligands, right? Which have
It's
strong,
the
strong,
thing.
strong,
Yeah,
which
it
might
really-
increase spin orbit coupling. And then this problem with dark triplet maybe will be not as bad because it will be
What
very
we
strong
see
coupled with
is
singlets.
some of the intermediate complex, it already has bromo. Actually, it quenches the emission. When the bromine is gone, because you already have a quite a heavy metal, either ruthenium or uridium. Then when you add the even heavier one, the thing is spin orbital coupling, you enhance the S1 T1 interaction. You also enhance the T1 and S0 interaction. So this
Which is
non-radiative, yes, that's right. That actually increases the non-radiative decay from the T1 to S0. That's not what we want.
So then it looks like you really, like, again, to think about the strategy, which we probably should go, is more on really thinking about lowering down as much as possible the triplet, and also as one state should be bright as well, because then we have a hope that they will be coupled.
See, the emission quantum yield, that one actually is related to how fast your radiative decay rate is also related to the non-radiative decay. In order to enhance the emission quantum yield, either you increase, it's better, best way is increase the radiative decay rate and meanwhile decrease the non-radiative decay.
But if your low state is bright, if you have a low state triplet state, which is of course not just localized on a metal, right? We expect it to be very hybridized with some MLCT, LCT, and so on, some charge transfer character, but a lot of coming from a ligand and pi kind of contribution. And again, which probably means that, my understanding is this, if you have S1 state which is bright, let's say if we talk about conjugated polymers,
Right.
they do have the bright state, I mean the low state is bright, that's why the emission is so good.
That's fluorescence.
Yeah, but it's singlet. Now, if they would have, and there are of course some triplet states there, which you usually don't populate at room temperature because the spin orbit is very weak in conjugated
That's
polymers.
right. Yeah.
Now, in our case, we usually have for ruthenium complexes and even for iridium complexes, usually the low state is not optically active in a singlet.
Right.
So then, if we have triplet which is coupled with dark state, then it's your, non-radiative pathway. If triplet is coupled to the bright state, and it moving
Your
down
thing
as
is
much as
maybe
possible, right?
S2 will be coupled with T1 or T2. It's just not coupled with the dark state.
No, this is well, yeah, but the point is that we want probably to move energetic both of singlet and triplet, right? And probably try to make the low singlet state also as bright, not only triplet, because then it probably will provide an increase in triplet emission as well.
Yeah, certainly. I think the stronger coupling between S1 and T1, when S1 is bright, yeah, it will enhance the emission quantum yield.
But on the other hand, we usually moving this to the red because it is
Most
MLCT.
will be lower.
Because it's MLCT and usually it's not bright. Like
Yeah.
again, we go into the lowest singlet states in absorption, usually not very.
Yeah, it's quite a weak.
Yeah.
Yeah.
And if they're bright, they're usually blue shifted.
So that's what I'm thinking. Yeah, this certainly is in principle. If we can control this, then will enhance the emission quantum yield. But on the other hand, if we can slow down the non-radiative decay from the T1 state, that even we do not really enhance the radiative decay rate, but we slow down the non-radiative decay, that actually also increases the emission quantum yield.
And to do this, the only way to do this, we need to decouple this lowest non-radiative states, which are always there, right, from those who are bright, and to decouple it through what kind of effects? In this case, only if this low state would be really much stronger localized on some portion of the molecule, and the bright state would be localized or delocalized, but completely on a different part of the molecule. Then you probably expect that they will be not as coupled, and that's why this non-radiative kind of channel will be not as efficient if you have both states very delocalized over the entire molecule, and then the coupling is very strong between them. So something like that. I mean, again, this is of course in experiment you cannot really see where they're localized, but with computations we probably can see this factor, localization of the orbital, and probably the low state, which usually not optically active or very weakly optically active, if they localized on a different part of a molecule comparing to the bright states, this would be probably a good idea to do, or at least to use it as a parameter for hoping that this helps to improve the emission.
That's, yeah. I mean, empirically, what photochemistry knows is in order to enhance the radiative decay, try to reduce the distortion of the geometry, that's another method, or make the ligand, the whole molecule, more rigid. So
or go to completely symmetric structures. Like if you use
that's what I try to say is, for this being star-dented ligand is ruthenium complex, the geometry is more distorted from the octahedral structure. So ruthenium one, this is less emission.
This is very interesting.
Iridium will be more bright. Iridium complex with this being star-dented ligand, yeah,
so actually,
it's less distorted.
The symmetry of the ligands which you use by themselves do not really dictate the actual symmetry of that octahedral structure. And in your case, it's really very important to have nice octahedral structure.
Yes,
not
less distortion, more rigid, increase the rigidity and decrease the distortion will enhance the emission.
And which bond is longer? Ruthenium, this one really I can answer.
Yeah, I did not pay close attention.
Nitrogen, ruthenium versus iridium.
I haven't
nitrogen.
looked at the same structure with different metals.
I was even trying to
You
look
were
on.
not doing rutheniums, it was Jabbat who was doing it?
He did not do the ruthenium. Jabbat and
Ben.
Peng. Yeah,
And Peng.
Yeah, Peng did.
And even if you had them, you should compare within the same structure with the metal, the only difference. So like if for the first tris.
I just still have a feeling like iridium, wherever nitrogen or iridium carbon bond probably longer by nature.
That's right. That's what I put.
Rather than ruthenium. And again, because they're kind of, you have more flexibility to build not perturbed octahedral structure.
Right.
If they're too short, not enough space
to move around.
and that's why it's kind of corrugates the molecule, like really.
But you could also have that if it's too large, because
Well.
the bond angles are pretty strict.
No, but then it would be not stable, right? I mean, like you still need to have a very good coordination in terms
Yes.
of bond. You really create a bond.
But you need an ideal bond length. So you can either be too small and everything has to crunch in, or too large and have it crunch out.
No, but my point is because the ideal bond with ruthenium is probably smaller.
Sure.
It just doesn't have enough space for the molecule to kind of align in a space so not perturb this octahedral structure.
Yes.
And you kind of really have to squeeze your benzene rings or bipyridine rings.
Yeah.
And in iridium it's probably easy to push them so without changing the ligands by
So
themselves.
I had a question about the topic somewhat before this. When you were talking about coupling between the singlet and triplets, technically we cannot just take the overlap to get the spatial distribution between singlet and triplet. But if you go with like Fermi's golden rule, if you assume that your spatial locality of your singlet and triplet are close, shouldn't that have higher coupling than if they're on separate portions of the molecule?
This is what we discussed.
So
just
could
before.
you do like what we did for spin density and say if
Charge transfer.
it's charge transfer or if it's pi star, could that be a way to go just from DFT versus having to do T to DFT or XOR corrections or anything else for like a screening process?
That part I cannot answer. Svelana, do you have an answer for?
Well, this is actually the question which we need to address.
Okay.
Just based
That's
on the
where-
simplified
what
models,
we're
you're
going
of
to
course
find,
expecting that if you have not overlapping orbitals in a space, then when you couple them through the spin orbit or wherever, right, this coupling will be reduced because of the nature of orbitals, right? Because again, when you talk about coupling, don't forget, you write your Hamiltonian, right? And you will have a part in the Hamiltonian of the spin orbit. But technically then this part of the Hamiltonian will be acting on a specific orbital. And couplings we are talking about the matrix elements after you already act of your spin orbit on the wave function.
Diagonal?
Huh?
Diagonal?
It might be not that well diagonal because you find in observables means you find the expectation value, right? So wherever you operate and then you have wave functions right and left wave function.
Yeah, that's
this is a formula
generally
for the emission for
from the
for
triplet
rates,
inside
right?
state. Yeah, it's
What's-
related to the intersystem crossing
Oh,
quantum
KR.
yield. Yeah, KR is a radiative decay rate constant. KNR is a non-radiative.
Yeah, but what I'm trying to say to Levi that we will have the coupling, spin orbit coupling as introduced in a Hamiltonian, right? Let's call it. And then the couplings we are talking about would be really acting on, let's say, wave function corresponding to the state 1 and wherever it can be triplet, singlet, doesn't matter, now it's coupled, right? So which means that again you will have, so kind of you modify already your regular, not ground state, it can be excited state wave function, but without the spin orbit, right? So let's say this would be just singlet wave function if you're not having the spin orbit coupling. But after you acting your operator on this, you're changing it. And of course, the nature where this orbital is localized will be modified or will be kind of end up with the different values of your coupling independent of this part, right? Just depending on the wave function, you will end up with something big or something small as observable, as actual value for this matrix element. Make sense? So this is answer to you that you can get very accurate way to introduce your spin orbit couplings. It's one thing, which again we usually don't. And this is a big question, how accurately you can really make this part of the including this spin orbit coupling. I don't know why I call it this. It should be SO.
Okay.
And the next question is, what is the nature of the orbital which will make your average kind of value large or small? And this completely depends on the of your low state which you are talking about after you are acting and mixing them singlets and triplets.
Yeah, I think that's really useful.
That's useful,
Discussion. Yeah, it's
For the strategy, how we gonna...
right.
Because on the top, I think your phi is really the matrix element, not just the part of the operator itself, right? So it's a value
That's right.
which depends on the, or which already depends not just on the how you introduce your spin orbit coupling, but really depends on the nature of these orbitals you are acting on.
So it's an open question if we can
How to calculate it.
highly approximate that.
Yeah. And again, you can look on them without spin orbit, just looking on singlet triplet, right? And we probably need to calculate with inclusion of some spin orbit couplings in whatever approximations are available to us, and kind of compare and get and answer these questions. What would be kind of really, do we really see this difference between singlet and triplet as we expect? That if what we expect, that singlet, like the low singlet dark one localized versus the triplet delocalized. Whether it really provides kind of uncoupled states, or they might not really so significantly impacting the outcome if you really include the spin orbit couplings accurately, or at least to some degree accuracy.
So regarding the structures, those are the three type of structures. Iridium, ruthenium, they are both octahedral structure. We can either use the 3 bidentate ligand, and the bidentate ligand could be diimine ligand or CN ligand. There are, and those ligand we can do variety of structural modifications by introducing electron donating or electron withdrawing group, or by extend the pi conjugation. Talking about extending the pi conjugation, there are two general ways. One way is we can introduce pi conjugated substituent through single bond or triple bond or double bond. Okay, those will impact the excited state properties. Impact everything.
I have a question. Usually, when you're doing the increase in the pi conjugation, you really usually do it like with platinum. I remember we were kind of increasing either top or the legs,
Right.
because they're flat. For the ruthenium or iridium, again, it's usually one ligand is increasing and another is not really changed. So is it because of the steric kind of question, or just for better control? Because again, if we're looking for the better symmetry,
Right.
maybe it makes sense to increase the conjugation in all directions.
We tried that, you remember? The thing is, when we increase the pi conjugation on both the CN ligand and the diimine ligand on the trace bidentate iridium complexes, we basically adjust both HOMO and LOMO.
What are you doing this way?
No, this is another way. That's by benzoannulation. What he just
Yeah.
did
This is
there
what
is a
recently we were
DPPN.
doing. This is
Oh,
what
yeah.
we were working on a paper with benzoannulation.
That's the benzoannulation. That's a different way. I haven't come to that point. Yeah, here we talk about extend the pi conjugation. Let's see.
Oh, we can't see it.
Yeah, I know. Let me just draw a little bit. Okay, for example, we extend the pi conjugation. R here could be pi conjugated group. It could be connected here, triple bond. We have the electron, the pi system, for example, here is a fluorine. And the fluorine here, we could have donor acceptor.
Oh, and when you, the other thing, you also need, if you want to increase the emission, we also need probably to increase the dipole, this, kind of push-pull rule, to have the donor acceptor how it goes, the acceptor and
we
donor.
tried that before. I think on the platinum complex, when we introduce a strong electron donating group, we basically completely quench the emission. That's the thing is for the
But should it
emitting
be
state.
simultaneously? You should have a kind of a good donor and good acceptor on both sides, not just donor or just acceptor.
We tried both donor acceptor. We actually had, I remember we had a system on the platinum complex. We have donor and acceptor. It
So
did
you
not
had
have.
a donor and acceptor at the same
Not
time,
on different
on the ligand.
different ligand. We can put
Oh,
a donor
different ligand.
here, yeah, on the splenouric call this arm, call this leg. We put a donor on the arm and the acceptor on the leg, or vice versa. It quench, I think, the quenches the emission.
Mhm.
Yeah,
So that's what we can play with.
yeah. Anyway, so that's one way to extend the pi conjugation is by a single or triple or double bond. Here could be, yeah, the triple bond, that could be a single bond connection, or it could be a double bond connection to attach the pi conjugated substituents on the core ligand. And the effect on the diimine ligand and on the same ligand is different. What we found is when we do this, using this approach on the diimine ligand, it actually causes the right shift and makes the triplet state longer lived. But when we try to do the similar, even quite similar substituents, the pi conjugated substituents on the CN ligand, it basically, yes, it makes the triplet lowest triplet excited state shorter lived. It because when we just do this on the diimine ligand, the lowest triplet state is this diimine ligand localized pi star. But when we also
Then it's
increase,
completely spread.
it mix more of the charge transfer character into the lowest pi star state. It becomes a configurationally mixed pi star and a charge transfer. Then the lifetime becomes shorter. Yeah.
And it's also blue shifting instead of red
Blue
shifting.
shifting.
I remember
with,
there was something,
no,
some
not,
paper
not
where we
too
saying
much.
if you do this, then it's red
No,
shifting.
no, no.
If you do that-
That's the other one. It come back to the benzoannulation
Ah, oh,
approach.
okay.
Okay. So this part clear to everyone, at least you
Well,
have
it's
a little
getting
bit
pretty
idea.
huge ligand in this case.
Yeah, that's right.
Yeah.
Then there is another way to extend the pi conjugation.
The beauty of this, you can start with a small, then slightly
Then you
increase,
just-
slightly increase, and then you can really go
That's
through
right.
as much as you could.
Yeah.
So means we will be probably restricted in really doing very, very long conjugated kind
Right.
of things. But
there's
we
some
probably will see the
steric
trend right
problems
away.
start. The steric problems start as soon as you start to increase the ligands.
No,
They are on the opposite side.
autohedral.
The ol-
Autohedral.
They are in a
They will
periphery-
rotate to try to
in a
avoid
periphery,
the,
in a periphery. Like they not
Periphery.
really contribute to the octahedral.
yeah, it's not on the
the only times that it does is if you do benzoannulation
yeah, this is
on
what I'm
a specific point. So not where the
You mean these?
nitrogens are,
Mm-hmm.
but the carbon next to the nitrogen and up. So on like, if this is the nitrogen, these positions, if you grow this way, that's the only time it really hinders because it grows towards the ligands. So if you grow anywhere else, other than that position, it's fine.
So it's okay.
So the benzoannulation, that's what just Dimitri drew is, that's another approach to extend the pi conjugation, doing the benzoannulation, add more of the, fuse more of the benzene rings on the diimine or the CN ligand.
So Dr. Soon, going back to Dimitri's question where he was saying, why can't you just do it on a lot of places? And you said that at that point we had both of them like grow oddly. Do you remember
They
his?
compete
Yeah.
kind of, yeah.
So
And it's actually quench emission.
Quench, yes, that's emission part. Let me see. Okay, yeah, emission was reduced.
but couldn't we use the overlap to selectively tune both the LUMO and HOMO towards each other if we do it on different ligands?
Okay,
Yes,
saying,
you certainly
like
can
if you
do
know
it.
that one ligand is really kind of contribute to your luma and another ligand to your HOMA and kind of pushing luma down and HOMA up, Can we play with,
Yeah, that we
with
certainly.
just different ligands and modifying different ligands to
That's
come them closer.
what we're going to do,
If
right?
we do not change the nature of the lowest triplet excited state, yes, you want to right shift the emission band, that's not a problem. But the thing is, when it goes to a certain point, then it started to mix the charge transfer with the pipette start. Then it becomes, you are changing the percentage of the lowest triplet excited state. It's a completely different story. So that's the thing is, yeah, there are certain range you can do it.
And
I
is
don't-
like 3 rings about the time where you go from charge transfer to pipette start?
It's hard to tell.
Okay.
It's hard to tell. Again, it's related to the diimine ligand, CN ligand. There is a balance. It's how initially the charge transfer and the pipette start they are separated. In most cases, pipette start is the lowest. When the pi conjugation of the ligand is small.
I have kind of a request to you, probably just because I know in many papers we are kind of close. I should should know them as well as you. But maybe could you find the most, how say, representative paper, just one or two, on each point which you says like, oh, if we increase conjugation this way, then it's improving this.
There are 2 papers we dealt with this, or 2 or 3 papers. One paper is this HS applied material interfaces, 2013. That's the first one.
Respond, right?
No,
No?
with what?
13. I think it was
13. I
15
think.
I mean, it's a different. Oh,
Nambi,
we probably know that.
Nambi. That was the first paper on the iridium complex.
Ah.
Yeah. Then later we have a 2014 paper with that one I think is with Peng or also Nambi. Probably also Nambi. That one is on doing the benzoannulation on the diimine ligand. Those 5 complexes we were able to fix the nature. The nature of the T1 state is still the triplet MLCT. Then when we doing the benzoannulation on the diimine ligand, we basically gradually lower the triplet excited state. So we make it shorter-lived and less emissive.
But redshifted.
Yes, it was right-shifted. Then we had another paper is doing the benzoannulation on the CN ligand. When the CN ligand, but on the other hand, we have to keep a small diimine ligand. So we, when we gradually extend the pi conjugation on the CN ligand, when it's big enough, the triplet state was completely switched to this CN ligand pipette start state. It changes the nature. That is a different story. So that's what I'm thinking is this one, there could be one point, that's why we do this systematic, variation, especially the recent 3 papers, is benzoannulation. I also need to point out is doing the benzoannulation not always cause red shift. It could be blue shift depending on the site of the benzoannulation. What we found is, for this diimine ligand, when we do benzoannulation and this position, it causes blue shift. Okay, benzoannulation and that position, let me use a different color. This position, that position, or this position, okay, that causes red shift. Benzoannulation along the vertical line, like what we are currently doing here, no change.
That's interesting.
Yeah, it's also has on the CN ligand it less pronounced. For CN ligand, it depending on the benzoannulation, whether it's on the diimine ligand or on the phenol ring, it will have different effect.
So it means it's somehow anyway connected with the
It's
with the symmetry. You're going
That's
out
right,
of
definitely.
the symmetry as soon as you go on the side.
yeah. What Solana's group is doing is we consider start from the simplest bipyridine, and we look at because that's where the normal. Then depending on the symmetry of the benzoannulation set, the symmetry of the frontier molecular orbital, basically that's a normal. Then when we do the benzoannulation layer, we can consider is the interaction of the 1,3-butene diene, this part. Either the HOMO or the LUMO of this part interact with the HOMO or LUMO of that part. Then the symmetry, depending on the symmetry, it could be the HOMO of this one interact. If it's a HOMO-LUMO interaction, it basically increases the LUMO. If it's a LUMO of this interacting with the LUMO of that, it stabilizes the LUMO. It causes a redshift. Yeah, that one has been, we have 2 papers published. One paper published, the other one just submitted. It's quite consistent. Yeah. For the CN ligand doing the benzo annulation on the phenol or on the pyridine, it will have different effect, but it also has this site selective, effect.
But can you put these kind of rules like on a separate list? Because you already got these ideas. What positions shift what
right on the diene ligand, it looks like it's quite conclusive. We already know it's that position, this position is blue shift, this position no change, and those 2 are the identical position. This position or that position will cause red shift. That part looks like it's quite clear.
That's interesting.
I think in the past, what we focus more is on the triplet lifetime, quantum yield, and also the absorption. I need to come back to check. That's why I really need to provide you the information. It's not, I really carefully check how that impacts the emission. Because here we look at not just the absorption, also we look at the emission, infrared emission. Yep. So any other questions regarding the type of molecules we deal with?
So can you please, you already mentioned it, but can you summarize once again? So there are 2 ways to affect position of triplet state through the extension of conjugation length. One is benzoannulation, another is just adding conjugated groups through
single or
triple or double bond.
So how they compare, which one affects stronger? Well,
energetically, yes, that's a good question. In order to cause red or blue shift, it's a benzoannulation, because benzoannulation directly occurs on the core ligand. Attention pi conjugated substituent, it does not really impact the core ligand. Especially right now we are doing is the pi conjugated substituents. Those are pi donor, electron donating group, pi donor. It introduce more of the intraligand charge transfer character to the triplet inside state. That's why it mainly impacts the triplet lifetime.
It does.
And also, it does. Yeah. But it does not dramatically shift the energy of the triplet inside state.
So you have kind of 2 degrees of freedom. One to adjust energy, and another is adjust lifetime.
That's right. We have one system we have not published yet. We try to combine, select the appropriate the core ligand, not the most red-shifted one, because when it's too much red-shifted, the triplet lifetime gets too lower. Even you add pi conjugated ligand, you can make it a little bit longer lived, but not to the extent we want. So when we select appropriate core ligand, then add this pi conjugated substituents there, we can redshift the absorption and emission. Meanwhile, we keep a reasonable triplet lifetime. It's a balance.
And this is again a good way how we can simulate many different kind of
Right.
Yeah,
and then kind of do the combinations.
Exactly.
Right.
Combination.
And find this
Exactly. You need to sacrifice something in order to.
That's what
get
I need
the
to get from you. I mean, Dr. San can kind of give the main ideas, what mainly influence on that. Then you checked computationally some
Bigger field, bigger space.
The bigger space, and then based on that, we kind of extract some rules. And based on that, I generate, let's say, thousands of the molecules, keeping in mind these kind of rules. And then we can kind of virtually screen all of them and pick up the ones which we expect gonna be, the best ones. And then we can check them computationally, like go back to you, and if they kind
Sure,
of
what we
confirm the
expect.
computation that
What
they
is
are really
optimized, yeah.
they are optimized.
Because
then we
that's-
can go back to the synthesis and check
Right,
them
check.
experimentally.
Well, what we
Doesn't
already
mean-
found, Selena, you remember that was a paper on the platinum complex. We add 3, 1, 2, 3 repeating the fluorine, ethanol fluorine group. It's one each from 1 to 2, it probably causes redshift, but when it goes to 3, it did not. Or even the second one, it's just because the triplet state is defined in the first
It's not
part.
going to the
It did not
substituting
really
groups,
go
it's just
to
sitting on
first.
a kind of around the metal. I mean, the
That's
ligands
right.
which are coordinated directly with.
Yeah, it's just the ligand with the triple bond directly connected to the platinum. I think that should be the HOMO. HOMO is just localized on
And
that
this also
part.
explains, well, very much related to this
Benzoannulation.
benzoannulation, because then it's really pushing it to the bigger size of the molecule. I mean, through the entire.
Benzoannulation, depending, is still set dependent. So when we continuously add the benzene ring, and that position is still further redshift, and actually it changes the nature. It becomes, this part becomes the both homolomo localized on that part. Hotoloto, yeah, we talk about triplet excited states. And also the thing is, benzoannulation has a certain other limit is when it becomes too big, pi conjugate.
Steric effect as well, right?
Not just steric stability becomes a major issue.
Photostability.
Even the
Or
chemical
chemical
stability.
stability.
Both chemical and
But this is might be dealing with the steric repulsion.
yeah, it
So
could
like you're really
be.
breaking again the octahedral core.
Yeah, we have one system. You remember here we have here. Then we have a phenol ring on that position. Then it really twisted. It causes a blue shift. Yeah, that one really is a steric effect. But if you continuously adding that direction, that's okay.
I see, so it's
Yeah, we played with many things.
position.
That's right. We try to do this one side and try to do it on the other side. And I remember when we initially tried to do this, and we were unable to get this most pi conjugated one. I think it's a stability issue.
It's almost a graphene quantum dot.
But then it becomes probably too big and too rigid for feed to the octahedral structure.
Even the ligand itself is not stable enough.
Oh.
It decomposes.
Or even ligands by themselves.
Yeah. So, what
But
else?
that seems like these kind of ligands should be stable more or less. Come on,
No,
this,
it says, I think there are lots of it's called aromatic hydrocarbon molecules. When the rings goes to 6 phenol rings fused, it started to become unstable.
But what about the graphenes coming there? There are so many of them, and it's one of the most stable structures, actually, the strongest ones.
Yeah,
Why
why?
it works for them?
It become more delocalized.
Yeah, it becomes the
I try to recall it's for graphy. Do you know what is absorption? It's absorption extends
Graphene
to-
flakes
Yeah,
in the infrared.
infrared, right.
Oh, how to say, near infrared. Or kind of in between.
But it is tunable by size and
But if
values.
you go to bigger sizes, then it's quenched. It's really works only as a nanostructure
Nanostructure.
due to the very
okay.
strong
For
confinement.
larger it goes
Yeah. As soon as you get into bigger size,
red and more,
it's not
more to the
emitting
red and
anymore.
red and goes to like
And
radio.
And with graphene flakes, my understanding is it's still
Are
unclear.
you talking about the emission or the absorption?
Emission.
Emission.
They
How
do
about
emit.
the absorption?
But it's also probably redshifted, right? I mean, if
Yeah,
it's
that's
emitted in the
right.
infrared,
That's what I'm
absorption
thinking.
will be not
Well,
very
what
far
I'm
away.
thinking is the stability certainly is related to the homoloma level. Because you can have a very narrow homoloma gap with both quite high homo and lomo. Or you could have like this. What I'm thinking is the unstable one probably is both homoloma level are lower, so it could be either easy to be oxidized or reduced, even by air. By air should be oxidized means so.
But this is like, even with graphene flakes, the nature of its emission is not really clear. It might be defects and age effects, where you just making a defect in the conjugated structure and this makes it emittive. Or it really is a nanostructure due to the confinement effect of your completely delocalized pi orbital or something like this being confined in whatever your 1 nanometer size or something. So, but my understanding is that no one really have a clear
Idea
evidences of either it goes this mechanism or that mechanism, because in these sizes it's very hard to control the defects or anything. There might be some defects due to hydrogen oxide, like I said, like they might be also very easily to oxidize or something, and you might have just kind of a chemical
what you are
defect on
really
the
looking at
surface.
is not the original structure.
Right.
Great.
But technically, if you increase the conjugation to the graphene kind of, then you're not really expected to be emittive at all, right? Because graphenes are not emitting.
It's a limiting case.
As I said, it depends on the pair conjugation. The 6th or the 7-membered ring, I mean, then probably the energy level is very easy to be oxidized or reduced.
So you
when you
already have
pass
this
that, yeah, that's right. As I said, if it become highly conjugated, then both your homoloma are so high, then stable.
There was a question I'm confused about, just how to think in the right way. So for method which is opposite to benzoylation, this linear extension of conjugated length, which changes lifetime. So is it longer chain,
Longer
lifetime, or opposite? And it is
Longer
radiative,
lifetime.
or non-radiative?
radiative lifetime. But radiation is not very high, right, in this case, intensity.
I think the emission actually it was also longer lived.
So when the
But the
charge
intensity
density
of emission.
goes away on this conjugated tail, it's less opportunity to interact, therefore
It doesn't go to the tails. This is exactly the point. Otherwise, we will change the energy.
but
So-
No, it's the intraligand charge transfer. The triplet
For the
state.
triplet state.
Yes, it's a mixture of pipette star and intraligand charge
so
transfer.
electrons
the
and holes
edges,
do
yes,
not
from
do
the
not-
edge to the
do not
center.
interact and therefore combine much longer. Longer tail, longer lifetime.
Yes, that's
It's
what
because
we
electron
found. But
hole-
there is a limit. You remember we also have one work we not published. I think it's Jebba did the calculation. We have 1 fluorine, 2 fluorine, and 3 fluorine. I think that one I do not recall my general impression was there was no significant right shift at least from the energy. So maybe still it's only the first pi substituents really take over.
Important.
Then
If you you have a limit, if you increase it more, it's not really
that's
affecting
not
it.
really, yeah, that's right.
Longer chain, longer lifetime.
Up to some limit.
Up to some, yes,
Very good.
yeah.
Okay.
So any
Thank you.
questions from the students? I think, when we talk about, every month we keep talking about this, they will get some idea.
But I think because it was so many published already by Weifeng, and we're also doing some computations. So I guess if you just go to the papers and you can focus just on recent ones, you will learn a lot just for reading
the
these
publication
papers.
list I provided to you, to the group.
Yeah,
So-
to all of us.
And
Yeah.
maybe create.
I sent it to Levi because he was asking.
Let's create a list of all participants so that one can send
The
things by one
You
click.
mean the literature which you sent? The list of
Yeah,
literature?
the list of
Our
papers.
publication
List of
related
papers.
But not only for the papers, for like announcements and.
Oh, just the group for us. Yeah. You mean all of us, or who is involved in the project?
Who involved in the
project. Okay.
I certainly, the list I gave it to you, was that in early this year or it was
You
after the
gave me
grant?
2 times the same list
Oh,
you gave
okay.
me. Yeah. I was asking like last year.
Oh, okay.
send me-
This
and
year it
this
certainly
year
has a
you
certain
send me the same.
update.
Ah,
Yeah.
you
Okay.
sent it updated one?
I
Because I
think,
wasn't
yeah,
really,
in June,
deeply-
it got to be after this grant started.
After this grant, you sent me like in September.
Okay, then
of
it
discussion.
closed. We probably have
Okay,
a
you
few
updated
more
it.
pages.
That was already so quick.
Okay, then.
I rushed them through to try and get back. I don't
Instead
know.
of 3 hours, we're doing less than 1 hour. Wow.
13
Then
minutes.
okay, so I don't have anything to discuss yet, because from my side, I don't have any updates yet. Since they are still working on the database,
Actually,
it's
I
not
have
ready.
a question about this literature. Should we, because you kind of already give us a good review on the way how different substitution, how we can, how say, split different types of substitutions with conjugation this way or that way, iridium versus ruthenium, and kind of difference and some similarities. So would it be a good idea to try to organize now all these papers to the this kind of ideas papers where we're really addressing this question of showing this type of conjugation is doing this, this type of conjugation doing that, this type of things for ruthenium, or this is comparing ruthenium versus ruthenium. So kind of really make all the published work already in a more organized way and make it to be in a clusters
Easy
of
to-
some kind of subsections or something.
You want to have first of all separately by each metal, and then
Separation
inside
by
of
metal
each
is
group-
very easy because
No,
it just
and then
from the
inside
name,
of
from
each
the title,
group,
right?
there's some kind of
But I would say
trends.
it's more like really on the. I mean, this is just by title. You don't need to read even the paper. You just say, "Oh, this is ruthenium. This is iridium. Can be done probably automatically through the keywords or something." But the main conclusions which paper is talking about, right? And sometimes, if it's in the beginning, sometimes we're not making it very pronounced because we're not sure 100%. Like if we just start working on these modifications, but after several publications, we really make it very clear that this type of changes really leads to that, and that. This is really
Okay,
inside the paper, and sometimes
that's-
it's not in the abstracts. Like you really need to read the paper carefully and kind of figure out what exactly this or that.
So, like, you would organize it in a way to almost write like a review to say.
Not just
if
review,
we
but
do
organize
this-
it in a way how we think was talking today, saying
Yes.
if we do
So
this,
if you
we
do
see that
benzoylation,
lifetime is
you do
increasing, but
this,
energy is
and blah, blah.
decreasing, or something like that.
Right, so benzoylation does these specific things on these positions. If you do electron donating, it does this.
So kind of thinking about table, and you having the effects on energy, lifetime, intensity of emission, I don't know, whatever other parameters we want.
Levi, you have this
And then
list.
kind
Can
of-
you do that quickly? You
then
read
we
these
can do
papers or
the-
not yet?
Well, some of them.
I
Much
It's about
smaller
70
parts.
papers.
Yeah,
so-
it's a huge number of
I
papers
went
already.
through to look at the computation methodology. So I split them into like which functionals they had.
Ah, okay.
But I didn't like go through and read the entire
What kind of
thing.
conclusions they got? You didn't. Okay.
But again, I think this probably has to be done more than just by one person. It's too much to go with
So
one
many,
person.
right.
And we probably need some expertise from experimental side as well.
Right, because and the person should understand here quantum chemistry in order to discuss this kind of stuff.
And I say like kind of the way how you explain it today, just really organize them in a pretty much similar way, but with kind of
Yeah, I can
Focus
ask
for each
Riza
paper.
because he is more or less experienced in this way among all the other guys I have
So
right
who
now.
is Riza?
Riza is the graduated from physics department.
No, he was here.
He gone?
it's yours.
Oh, okay.
It's mine.
So he graduated from NDSU physics.
And JSU
Oh,
physics
okay.
department.
Who was his advisor?
The Alexander.
Oh, okay.
Okay, so thanks.
Yes, that's what I said. I'm not prepared.
Thank you much. It was
Yeah, that's good. That's what we wanted actually. That's
Okay,
right.
that's
yeah,
good.
Yeah. Because to get some understanding of what kind of trends we have if we change this, if we change this in there.
Actually, we force you to give us a lecture without preparation.
And without preparation, really.
It's like
That's the thing is you just look at it so many times. That's my job is to try to organize and try to find out come the
The trends.
rules. Yeah, the trends.
You know, the idea anyway at the end to get this kind of fill out this kind of table. So where we have information about the the overall material, right? We have information about the what kind of metal, what kind of ligand, or maybe there are several ligands, and the properties for them. So if we calculated data for the whole the metal organic complex. So we put the information over here, so it's going to be kind of several kind of properties. And then using some cheminformatics methods, I can complete separate sites, like say properties for each ligand, for example. Then based on that, I can do all this virtual screening. Right. So I need the properties for the whole system, and then the properties for each ligand.
So you expect that someone will calculate it for you, or you expect your students will do it?
I expect that you at least will calculate the whole.
Because some of our papers have calculations of the ligand by themselves, right? I remember it was a
some
few.
of those,
We were doing
So
absorption spectra at least for just ligands.
Separate ligands.
Separate ligands,
You
yeah.
look at
But there
them.
were a few of them because usually it's very kind of trivial, or it was done already by someone and we just refer to the papers. But this is much easier than the whole thing, so probably not a big deal to calculate.
Yeah, for ligands, it's not going to be a problem at all. The main thing
Especially
what I'm
many of
expecting-
them are repeating, so it means we don't need to calculate. If we have, suppose, I don't know how many, 70 times 5 at least, right? 350 complexes so far, or more than this?
Oh, more than that.
700?
Oh, not that much.
So in between
Yeah, even
300 and
350, it's
700.
going to be okay.
Around 500 probably complexes, so, but we probably have twice or maybe 3 times less of ligands because with
Some of the
modification.
ligand, yeah, we use that for both the iridium, platinum, and also ruthenium.
So that's why the field of ligands is not
No,
is small, of course, comparing to the entire thing.
The field of ligands which you used, but we can kind of theoretically generate.
We talk about how say main site of ligands, and then if you put the
The main core
substitution.
of the ligand and then
Well,
these
again, this is
R
we need to
groups
define
attached.
with our language probably, because this is what took me also some time to remember. Like I was saying, you saying, oh, it's a interligand transition. I'm saying, no, it's just pi transition because it's one ligand, and we're saying, no, it's 2 ligands. Like it's
Yeah,
like
because they are connected.
this is what we call arms, right? So the central part, the core,
the
which is
core.
coordinated, is a ligand, and then the
Peripheral
substitution to it is supposed to be a different ligand, or the
It's still
substituting
same
group,
ligand, we call it intraligand charge transfer.
or whatever.
Yeah, it's actually still peptide star transition in nature. It's just from one part
Yeah.
of the ligand to
But
the
my
other
point is,
part.
we also need to be careful what we call exactly the ligand, because with this modification, we might really use in different.
Yeah, then we have
how
to
say,
kind of
think about
discuss and
different
put
things.
this kind of abbreviation in between us to understand, right?
Yeah, when we really talk about ligand to ligand charge transfer means it's from one ligand to the other
Coordinated ligand to the from coordinate ligand
Yeah,
which is coordinated with iridium to another ligand coordinated with iridium, and intraligand it means
The
it's
same ligand,
part
different part of the
of the
same
one
ligand.
ligand which
you
is
see there
coordinated.
are kind of several interesting
Features,
features.
small things,
right.
yes.
So,
Yeah.
are your property 1, whatever, are those for the entire system or for the ligand?
No, for the entire system, it's over here.
And then the ones between that and
This
that's
one?
for each ligand?
Per each ligand, for example, that's a property for a separate ligand.
So
Yeah.
for if you have 2 different types of ligands coordinated to the same metal, you would have
Then it's going to be here, the second
Properties
one.
from ligand.
That's the
one,
first
properties
ligand,
from
that's the first ligand, that's the second ligand over
so,
here.
but you have like 2 CN ligands and 1 NN ligand, so you would have 3 ligands that you're going to characterize.
But if CN
Right.
is the same, if it's
Yeah,
the same, then it
typically
would be
they are
2.
Right.
Yes, but it might have slightly different if you do not use symmetry in the calculations.
If it's isolated ligand, it would be the same, right?
Okay.
It changes its symmetry only due to the interaction with iridium.
Yes,
Or with
except
ruthenium.
if the NN ligand is not symmetric. So in the paper
Yeah,
that we
so
just
far
did.
we are using, there are a few systems we are really using asymmetrical. We call it mono-substitute, and only one pyridine ring has a substitute.
Which then you have to characterize all three.
No, in that case, it's
Oh,
still just
maybe,
two.
I think,
No,
Thin ligand are still the same.
I don't know, but
Oh,
maybe
you are saying
it
it's
So in
sounds
the paper
useful.
that we just did, the
You need
review-
probably to make like
I did
this
a review
isolated
on.
ligands, you probably would
We
be
had to look at both.
separated into
The
core
one that
ligands,
had
which are coordinated.
quinoline,
And then the
that-
ligands, when we start
that was
substituting,
different compared
like
to
what
the
Rebecca
one
saying,
that
like
had
for example,
the
conjugation,
pirate-
shorts, longer,
pirate.
longer, longer.
That's
So it looks like you
right.
need probably
So
to
you
split
still
it
have
into
to
the
do all three.
core ligands, which are coordinated, and there would be really smaller number of such guys. And then
But
with modification on
effect of
as
the
substituting
NN
groups.
ligands in
Right,
Which
we
are
can
added
call it
to
like
the core
AX,
ligands.
for example.
Huh?
Okay.
AX, for example, the core is A,
Philip-
and X is kind of
Yeah, something like
replaceable,
that.
the ligand. But that's
And
a
then you
whole
will have kind of
AX.
some kind of space for your A ligands and then X substituting
Right.
one, and then you put them together, and it would be your kind of you probably need to include kind of to separate it, not just ligands, and then whatever
I
our changes make you a different ligand. It probably should be substituting groups. Let's call them X, and core ligands. Let's call them A, and then whatever the possible combination between A and X.
Yeah, we can add like one more.
And then
the
all
column
possible
over
combinations between AX and metals.
Here. Yeah, that's right. Yeah, let me put it actually. That's no problem.
So, these are the, and they're not the same. And that's because of the quinoline group induces a
Yeah, he's talking
structural.
about the same, but the structure is
Oh. So the quinoline group here induces a change. This ligand.
Oh, because this,
that it
yes,
does
because you
not
have
change.
not symmetric
Mhm.
these
Yes.
buffers, yeah.
So, database-wise, wouldn't it be more rigorous to compute everything for each ligand instead of having to go back? So, like, if you didn't realize this and you just computed for one like the two ligands, the CN ligand and the NN ligand.
No, this was saying like he needs to put additional
Okay.
separate thing, let's say core ligands, right? And then ligands which you use for substitution. And then wherever, like when then you put them together, it would be AX ligand.
Okay.
And then we can avoid this problem what you're saying, right? Because depends how you add this.
Those are still different. What you are talking about is a core ligand is still symmetrically substituted. He's talking about if the core ligand is asymmetric, then the C ligand, even the ligand itself,
No,
look
but they
the
will be
same.
different only due to the when they are interacting on a ligand.
Right.
By the, like if you just look on just ligands by
Ligand
themselves,
by
they would be the
itself,
same.
it should be the same.
Yeah,
That's
it's
right.
it's only due to the interaction, and then of course how
Yeah.
you
So
attach it.
After
it's like the
coordination,
dihedral is less than like angst.
Yeah, this will go to this other column where he's
Okay.
having the whole system.
I just wanted to make sure that we wouldn't have to go back
We
and
probably
recompute
we will,
stuff.
we probably will have to do it anyway. At some point, something will be missed, and we have to redo or something like this. Yeah.
Okay, so
Oh, I have
Are we
seen
done?
this figure.
you have seen?
Dots.
Yeah, so these
Repetition
just a
helps to
schematic.
memorize.
Yeah, I kind of repeating everything. So.
For educational purposes.
Right. When you're several times repeating the same stuff, it's kind of easier to memorize, right? To understand something. So these two sides gonna be some experimental data for one side, from group of Dr. Sun, and the modeling stuff from Dr. Killian and Dr. Killian's group, right? So, and then we will put together this kind of thing to find some trends. It's kind of the regular strategy for this kind of works.
No feedback loop.
Feedback loop is there, but I put it somewhere earlier, right? I don't know.
I think
Okay, so it's here.
Okay. Yep.
So this kind of. There are gonna be some small loop over here, actually, right? Since when we did some modeling, got some kind of data, then giving you these ideas back, so you're trying to calculate them and see is that improving or not computationally, and then you're sending it back. So based on these new improved ideas, we are trying to do the virtual screening, and then goes to see. Actually, there should be something like that, like a connection between virtual screening and computational chemistry, and only after that the synthesis. So when you kind of prove it computationally and then send it to synthesis. And then it goes to the best candidate. Yeah, we have to think about that. I mean, how this loop can be modified. What is the best way to work? So it's actually going to be useful for some future steps or for some other similar works, but different compounds, different systems. Because still, kind of, no one was able to offer really ideal way to design this, even metal organic systems, to design them, not like one by one, but to do like virtual screening for thousands or millions of different hypothetical systems, and then kind of picking out the best ones. Still, no one was able to do that. And we just discussed, we have a meeting, so-called the Center for Bioplastics today. And just discussed with other guys that for the polymers also, no one was able to offer the mechanism how to do the like drug design, but for the polymers. So this is a problem. There are no QSAR for polymers, like well-working QSAR for polymers available yet.
For a project this size, how many papers would come out of something like this?
You mean regarding this particular project?
Yeah, like the size of
It depends on success. So it can be like few papers, 3, 5 papers, it can be 15, 20 papers. So it depends on the success within these 3 years. So we'll see. It's always kind of challenge. It's always challenge. We put from the reviewer's point of view, because as soon as we're submitting these kind of proposals, some reviewers kind of giving us feedbacks, and almost all of them say it's pretty ambitious. The proposal, the pretty ambitious project. They don't know how successful it's going to be. They told directly.
Yeah, it's a high risk,
high risk project.
Mm-hmm.
Okay.
But they wanted us to try, so that's why they kind of funded it. Mm-hmm. They wanted us to try, so we'll see. So even I have no idea is that going to be successful or not, because that's new for me. These kind of systems and this kind of loop idea. Let's see. But we have to try, because as soon as we be able to make it work, we can apply the same idea for different systems. And we will be really more or less sure it's going to work this way. Yeah. Okay, then thanks everybody for discussion, huh?
Yeah, next month.
December.
December,
but when cannot.
But you were leaving when?
December 3rd.
Oh, so early.
Coming back
Yeah,
January.
so the whole December, and then I'll probably in the middle of December also gonna be traveling.
If we need a meeting, this technology gives online connection if we need. so we can anyone with internet access can
But
be on the screen.
we need to decide probably the topic for the discussion, like what we are expecting to meet for.
Right,
What
I
is the
expect
reason?
something from the computational point of view. If you can present something, at least one work which you completed, and to show steps what you. Yeah,
All
for
our
example,
work which is published is completed. What do
right.
you mean completed?
What you published to give us idea how you do the calculations, what kind of
So it's
challenges you meet.
more the back end, what you do, instead of here's our results.
So you expect methodology or analysis of results?
The methodology from your side.
Oh, so you want us just kind of review how we
Methodology.
calculated, let's say, ruthenium, how we calculated the
Yeah, at least to
how we
start,
calculated platinum, are
right.
we using different,
on
like
the-
something what you were trying to do with
Yeah,
figuring
but-
out which functionals we are
Okay.
using and how they are different.
Yeah,
But the
just for the
same-
next, for the December,
But the
for
same
example.
functionals do not
Because
work for different methods.
Starting from January, I'm pretty sure we will have some structures already ready for you guys to give and start the calculations.
So then what time, if you want to meet in December?
In December.
Because we're also leaving just after
So
semester.
up to at least December 10, I'm gonna be here, so we can meet somewhere up to December 10, physically here, and send, for example, to Renfang
have exam
the
on
link,
December 10.
so she can virtually be with us. Or it's gonna be any day of December, but then I'm gonna be virtually.
So Tuesdays are
Renfang gonna
4th
be
and
virtually.
11th.
Tuesday of the dead week. That week would be 10 minus 7, 3. Actually, December 7 or 4.
So December 4.
So that would be the first Tuesday of December?
December 4. Okay,
For now, at least. Then we can,
I'm good.
if it doesn't work.
I'm good. Yeah, we can discuss.
Because Dr. Soon, you don't really need to know the.
Function.
Not really. I will be in the booking. So
But you can send it.
Yeah, because based on that, I may get some other ideas how I can
They have to be.
be involved, or how I can
Do you have
help
anyone
from this cheminformatics point
that's
of view.
way. He has a class.
Thank you.
Announcing completion of the meeting?
Yeah,
How
yeah,
to
yeah.
we are
We announce
talking
it.
about
Adjourn.
That's the question.
Okay, yeah.
He wants to know.
So meeting
He
is
wants to know it
complete.
would be useful if he
Thanks for
doesn't care.
joining.
Thank you. Thank you.
So I